I'm going to review this framework we've been developing throughout the last year. And to do this, I will tell you about 3 papers we've been working on. And I just want to mention the great collaborators in some of these papers, Yossi, Shai, Nadav, Philip, and Michal. So many applications rely on the fact that natural images, patches of natural images tend to recur a lot inside one single image. So small patches recur a lot, and this can be used for many things like image completion, for image denoising, like the non-local means, and visual summaries. But patches also recur across scales of an image. Sorry. And this was used for many tasks as far back as the 80s for a thing called fractal compression, and then for this set of works coming mainly from our lab at Weizmann in the last decade. And I think this image that you're seeing now is sort of misleading. It's a contrived image to make a point. The patches we are talking about are much smaller. There are 5 by 5 patches with very small features that tend to recur, and this is a very, very strong prior. In fact, this was empirically tested to be very strong and almost every reasonable visual data. And the great thing about all these methods is that they are totally unsupervised. You don't need any supervision or any pre-training for them. But the bad thing about them is that then since the year 2012 came the deep learning, and gradually it outperformed all of these tasks, be it denoising or super resolution or whatever. So deep learning was receiving much better results. So here is our line of thought. We were thinking, why don't we just take deep learning and the power of the internal statistics of natural images, combine them together into what we refer to as deep internal learning. And that means that we train an image-specific convnet, and we do it at test time and on the test image only. Now, this gives rise probably to 2 questions. The first one is, how can you train a network on just a single image? And the second one would be, how is it possible to do it fast enough during inference time? So I'll try to answer both of these questions. So the main thing to understand is that we like working with fully convolutional networks. And when you're working with a fully convolutional networks, then you have to understand that every pixel in the output is just a function of some patch in the input and not of the entire image. So actually, a fully convolutional network is actually just training on this bag of patches where each of them has its own output. And coming to think about it, the number of patches you have inside a single image is actually almost the number of patches, the number of pixels that you have in the image, since they are overlapping. So you can think of a fully convolutional network just as training on this huge batch of patches rather than training on this structural image. And the second question was, how can we do it fast enough? So here's the thing. So inside a single image, the entropy of the distribution of patches is much lower than the entropy of the patches from images from some external data set. This was actually empirically shown back ago by Maria Zontak and Michal Irani. So if you have much lower entropy, you can use a much lighter network, and that means you can train it much faster. For example, in the work that I'm just going to show you for the challenge of super resolution, using a fast GPU like V100 GPU, the training time and the inference time all together take less than 10 seconds to do the entire process. So this takes us to the first paper that I want to tell you about, and this is called ZeroShot super resolution, and this was the first example we used for this framework of deep internal learning, and this is with Nadav Cohen and Michal Irani. It was in the last CVPR. So up until recently, there was a very typical way of doing super resolution using deep learning. And this is how it was. So you have this big data set, consists of pairs of images, low resolution and high resolution, and you just take some network and you train it to generate the high resolution images from the low resolution images. And after you have it trained, and you train it for weeks or days or hours, it depends, then you can apply it to these new images you've never seen before, and now you can get your super resolution image at inference time. And this was first done at 2014, but then later there were tons of versions of super resolutions, and I'm mainly going to compare to this work called EDSR Plus, and this is almost the state of the art. There's a new one now, but this itself was very impressive, and got, in PSNR terms, it got about 2 dB improvement comparing to all the patch-based methods. However, there are two problems for this classical approach. So one would be that they only work well in what we refer to as ideal conditions. And ideal conditions mean that, first of all, they assume that the low resolution image was actually downscaled from the high resolution image using this known kernel. This is the bicube kernel, and this is what you get when you use MATLAB and you type IMResize. This is what you get. And then it was always the same for all the challenges and competitions for super resolution. This is how images were downscaled, and this is what they all assume. But this is highly non-realistic. When you take a picture with your camera, it doesn't happen this way. The second thing is about artifacts. They can't handle any noise, and we'll see it in a minute, that they can't handle noise or JPEG artifacts or anything of this type. The second problem is that they do not exploit well the internal information. I won't go into it, but you can ask me later about why can't they do that. So here's our approach for super resolution. And remember, our goal now is to train a network on just one single image. So given this input image that we want to apply super resolution to, we're going to do the counterintuitive thing. And instead of upscaling it, we're going to downscale it. And then we're going to take this low resolution image and we're going to feed it into this network, and we'll get what we're hoping is the super resolution of the low resolution of the original input image. So to make sure that this is indeed what we get, so we're going to use this loss, this autoencoder style loss, that says that we want the super resolution of the low resolution of I to be as close as possible to I. And remember, this is a fully convolutional network, and we're going to train it for a while. And once we have it trained, now we're going to take it and apply it to the original input image to get our super resolution. Fully convolutional networks don't care about the size of their input. They can be applied to any size of an image. Now, why would that such a thing work? So you have to remember what we started this talk with. So the distribution of patches that we have here in the low resolution image should be very similar to the distribution of patches that we have in the original input image. And keep in mind that we're using a fully convolutional network, so it learns how to deal with patches. It finds for every patch its solution, its super resolution solution, and it sees the same patches back again, this bag of patches, it meets the same patches here, or the patches from the same distribution, and it knows how to super resolve that. However, there is such a thing as internal overfitting, and to avoid that, this means that what's going to happen is we're going to get good reconstruction for the image, but we're not going to generalize to get super resolution as good as we might want. So in order to ameliorate this one, what we're going to do is use simply data augmentation. So instead of training on the original image, we're going to train on random augmentations of the original image, and this way we'll be able to avoid overfitting. So this is called oh, sorry, one quick comment about the downscaling. So the question arises, how do we downscale the image? We just mentioned that you don't want to downscale it the same way all the time. So there are two possibilities. One possibility is that we know the known kernel, for example, it is one of these competitions, and it's bicubic, or we're using camera and we can do some analysis on the camera specs. But the second option, which is more common, is that we don't know the downscaling kernel, in which case we're going to use this method by Tomer Michaeli and Michal Irani called blind super resolution that is able to estimate the downscaling kernel. And this is an internally based method as well. This is a patch-based method, and it doesn't need any additional data or anything else. So this is called, in short, ZSSR, zero-shot super resolution, and it has some really nice advantages. One of them would be that it can be applied to any data type. Externally trained networks are only applicable for the types of data they were trained for. Most of the times it's natural images, but we can also apply this on the fly, for example, for astronomy data, for microscopy data, whatever you want, just on the fly. Another thing that is that we're able to use any downscaling kernel, and we can estimate it on the fly. Externally trained networks are already trained. They can't retrain for a new kernel unless they train again for whatever it takes, you know, days or hours or whatever. ZSSR is robust to noise and artifacts, and we're going to see it in a minute. And lastly, you can decide the scale factors that you want to do super resolution to just on the fly. The thing is that you don't have this externally trained network for X3 super resolution or X4 super resolution or whatever. You can get to choose on the fly. So for example, you can even upscale your image, let's say in the horizontal dimension by 2.5 and in the vertical dimension maybe by 3.2. So this is why we say that this is the first work that actually does super resolution in the wild. So let's see a couple of results. So here's an input image that is checkpoint Charlie. This is a post-World War II. And applying the externally trained network state of the art at the time, EDSR plus, this is what we get. But applying ZSSR, we get this one. So this is the externally trained, internally, external, internal. Let me brag about this just a little bit more, and we'll look closely, and you can see how this is how the external looks like, and internally you get this new information. For example, the gap between this guy's legs over there, and some information on the back of the motorcycles. Here's another example, and this is an ideal case. This was downscaled bicubically from some ground truth image, and applying EDSR plus gives really nice results. This is X3 super resolution, and it can resolve some of the letters, which is really nice. But applying ZSSR gets much better results, and this is not surprising, since this is a very convenient example for ZSSR because it gets these examples in various sizes. And you can see, for example, how ZSSR ignores this, it doesn't create the artifacts in the S letter at the upper row, or if you see the bottom row, you can see we get much better letters. For example, look at the character at the bottom, at the G over here. We are able to identify that it is a G and not O or anything else. And this can also be verified numerically, since this has the ground truth. Here are some more examples, synthetic examples. We just randomized some kernels and downscaled. And so this is some kernel image was downscaled by, and this is how an ideal bicubic kernel looks like. And this is the result you get by EDSR plus. Now, estimating the kernel using the blind super resolution method gives a reasonable estimation, but not a perfect one. And we're using that with ZSSR, and this is the image that we get. And you can see much clearer details. And numerically, the difference is really big. In this particular case, we get something like exactly actually 3 dB of difference. There are some more examples. Here is what EDSR plus gives for this one. And you can see that we're able to find these bars. And these bars are not made up. These are true bars in the windows. And here's another example. And now we can see that this is a noisy example. Now, ZSSR doesn't know that there is noise in here. We are not modifying anything about the model of the noise. In this particular case, this is speckle noise. And EDSR plus actually enhances it. It enhances it because it enhances it because externally trained networks of super resolution just love high frequencies. When they see high frequencies, they grab them and they enhance them. And so this is why it's actually worse than the original. But ZSSR Plus is able to be robust to this noise and almost clean it entirely, but still keep these fine details in the image. Here is another example, this time with JPEG compression artifacts, and you can see that again EDSR Plus enhances them, while ZSSR is able to remove them almost completely and get a much better image. And basically what we see when we're using ZSSR is that for the ideal cases, when it was downscaled by cubically and no noise and other stuff like that, we get reasonably well. We get something that is comparable to the state of the art of about a year ago. But on the non-ideal cases, which are the real cases, we get a very significant, a huge improvement between 1 to 2 dB better than the current state of the art. So this is a real super resolution. And from here, I want to take you to our next work. And in this particular case, we wanted to take the logic of this internal learning and take it to generative adversarial networks. So this is a work called InGAN, stands for internal GAN. And this is with Shai Bagon, with Philip Isola, and Michal Irani. And here's the goal of what we wanted to achieve in this work. So let's say I have this input image right here. I want to change its size or to do some transformations, but I want the elements in the image to maintain their original shapes. For example, if I want to create a visual summary of this image, so I'll have this output right here, and you can see that this isn't just a squeezed image. You can see that the windows, for example, are the same size. We just have less of them, and you can see that we have less bars in this barn house in the back, but we just have we have less of them, but at the same size. We also might want to expand the image to make it bigger, and then we'll get this thing, and you can see that all the elements within the image are at the same size. We're just changing their decomposition. You may also want to change the aspect ratio in one direction or in another direction, and basically what we want to do is to preserve various element sizes and relative locations while globally modifying the image that we are handling. So here is our approach to it. Let's say I have this input image X and some output image Y. So maybe some of you are familiar with the thing called the bidirectional similarity criterion for image retargeting. And this says that all the patches in X should also be in Y and vice versa. But we want to do a much more general thing. So we're saying this. We want to have a distribution matching between the patches, the patch distribution of X and the patch distribution of Y. And we want this to be for all scales. And lastly, we want to preserve the relative locations. So for example, if I have the watermelons at the top of the image in the input, I also want to have them at the top of the image in the output. And reformulating these three requirements to just one single requirement would end up with this requirement. We want to have local distribution matching of patches in all scales. And this can be formulated as a conditional probability, saying that the condition is the relative location in the image. So how can we match this distribution? So over the past few years, there is a great way of learning distributions and drawing examples out of them. And of course, I'm talking about generative adversarial networks. But can we apply generative adversarial networks on image patches? So this is where the deep internal learning comes in. And you have to remember that we know that using fully convolutional networks, one image actually consists of tons of data. So if we combine this logic all together, we're getting what we refer to as an internal GAN. And that is, we train a GAN on a single natural image. So let's see how it works. So given this input image, we're going to feed it into the generator, but we're also going to feed the sizes that we want to rescale to, the height and width. And we're going to get these retargeted images that we're hoping that is good, but to make sure that it is good, we're going to feed it into the discriminator. Now, this is a patch discriminator, so it doesn't produce just a scalar like ordinary discriminators. It produces this map. And this map corresponds to the image by location. So because this is fully convolutional, every pixel on the discriminator map corresponds to its receptive field in the output image. So for example, if I have this white pixel, it means that this patch that it sees is very likely to be drawn out of the learned probability, and vice versa for black pixels. So we train the GAN as you would normally train a GAN, but we also have to train the discriminator, meaning we also need a real example. So our real example is actually just one example. It's the original input image. So but remember, this is not just one. You have to remember that the original input image consists of many patches. It has a lot of data. So basically what we want is to fool the discriminator. We want the discriminator not to be able to tell the difference between patches that came from the original image to patches that came from our generated image. So this is basically our GAN, but there is one more problem we have to refer to, and this is a very common problem with GANs, and I'm talking about mode collapse. So internal mode collapse is a thing, okay? Imagine, for example, what happens if the generator produces this image that does not contain this farmer over there or the bull. It just has this, grass and whatever there is there. The discriminator says, hey, that's great. I'm happy about that, because every patch that I see is a valid patch. Every patch here is drawn out of the learned distribution. So we have to make sure that we are not missing any information. So in order to do that, we're going to use this decoder, and we're going to use the decoder and try to reconstruct the original input image back again. And we're going to just use this regular L1 loss to make sure that we are doing it. And the thing is that if we're able to reconstruct the original input image back again, it means we haven't lost the information. We can find all the information in the output image to reconstruct from. And so the total loss of InGAN is the loss of the GAN plus the loss of the reconstruction, weighted, of course. Let's see some of the elements within InGAN. So the generator is just a unit architecture, which is very common these days, but it has this special layer. This is the layer that does the transformation. It's a parameter-free layer, and we have to feed it with the scales that we want. Now, during training, we're going to feed it with this with random scales, so it will be able to generalize. But in inference time, we're going to feed it with the desired scale that we want to retarget to. So let's see the discriminator. So remember that this is a patch discriminator. It is fully convolutional, and every pixel in the output map corresponds to a patch. And this is a multi-scale discriminator. I'm not going to get into too much details, but it works on all scales, and during training it works in this coarse to fine routine. Lastly, in the architecture, we need to mention the decoder. Now, the truth about the decoder is that the decoder is just another instance of the generator, only fed up with the inverse of the scales of the first instance. Now, when you think about it, this can be really efficient, because the second instance of the generator also performs this retargeting. The first instance receives always the same input image in the same size, but outputs differently sized images. But the second instance receives images in various sizes, but always produces an image in the same size. And the big advantage here is that it trains with L1 loss rather than with a GAN loss, which is less stable. And this stabilizes the entire system. So you may say that this part of the architecture is actually an autoencoder. But we're using the same encoder back again. So this is not an autoencoder. In fact, since we're here in Israel, we can actually say that this is an autoencoder. Okay, let's check out some results. So given this input corn cobs, we're able to stretch them, but it's not really stretching because we have new corn seeds that are now generated. And if we change the aspect ratio in a different dimension, what we're going to get is actually more corn cobs. But interestingly, no two corn cobs are alike. They are not just, it's not just duplication. What we get here is we generate new corn cobs that are drawn from this implicit corn cob distribution, and they are constructed from these corn seeds, which in turn are drawn from an implicit corn seed distribution. In fact, InGAN is able to be trained once and then to resize to any size and aspect ratio we want in real time, so we can produce this video of these smooth transitions, changing the size or aspect ratio of the images. And you can see how new corn seeds appear and disappear, and how new corn cobs appear and disappear while we are applying InGAN to the image. Here are some more examples, and these mainly talk about multiple texture synthesis. So you can see, for example, how new fruit appear and disappear, but also how new fruit crates, fruit boxes also appear and disappear when needed. And the same goes here with the windows of this building right here. You can see how new windows appear and disappear, and the global structure changes, but the local structures remain the same. These examples are about adding and removing big elements from the image, be it the penguins at the bottom or these poles in the upper side. We've made this comparison. I don't want to get into it too much. We made comparisons with the other works that do similar goals, and we find that there isn't another method that is able to do exactly what we do. Each has its own problems doing it. And here's some more comparisons, and this is a challenge for image summarization. And you can see that InGAN produces an image containing just one carrot, but it keeps its texture. And as we see, this is the best way to summarize the image above. It's not just cropping of the image, and it's not ruining the image as the other works. And here's another thing. This is changing the aspect ratio. It's a retargeting challenge. And you can see how InGAN actually preserves the size and aspect ratios of all these three birds. And moreover, the birds remain their original relative position in the image. For example, we have the bird that is in the upper left side of the image, etc. Here are some more examples, and you can see this is can be useful for dictators. You can enlarge their army, so you can see how we add more soldiers, and this is a sushi menu that I took a picture of when I was in Tokyo about a year ago, and this exemplifies the principle of this local distribution matching, because you see you have the area of the nigiri dishes and you have the area of the fotomaki rolled sushi dishes, and this is very obedient to the position in the image. Here's another example. This is the Capitol building, and you can see how more floors are added both in the sides and in the middle tower. And I just want to show you that it's not just resizing. We're also doing other things. For example, we can do these geometric transformations, as you can see in the left, and in the right you can see what happens when we introduce some noise into InGAN, and we do these very common things for GANs, this latent space interpolation, and just getting a couple of different versions of the same image with respect to some noise. Another thing we're able to do is a challenge called reshuffling. So let's say I have this image right here, and I want to take the guy and the bull, and I want to make them switch places. So I'm just going to crop them out of the image, and I'm going to put them on this noisy background, and I'm going to feed it into InGAN, and then I'm going to get this new image when the guy and the bull actually switch places. Okay, so the last paper that I want to talk about is a paper called Double Dip, where deep is DIP, stands for deep image prior. And this is with Yossi Gandelsman and with Michal Erani, and this is to be presented as an oral in CVPR this summer. And in order to understand double deep, first we have to talk about deep image prior. It's a work by Ulyanov et al. And it's really a cool idea. Let's say that we have this noisy image, and now what we're going to do, we're going to take a fully convolutional network, and we're going to feed it with this noise. This is a noisy image, not a noisy image, an image of noise. And this network is able to generate some image, and we're going to make it generate this noisy image. So we're going to use just an L2 loss, and we're going to just to say to the network, we want you to, with the same static noise, the noise doesn't change, just please generate this image. And I'm sure you all know that this is a very easy task. The network can do it pretty easily, just overfit and create this image. But the interesting thing is that if we stop the training at some point, then what we're going to get is the clean image. And the reason for that is that the noise is much harder for the network to learn, because the noise is not correlated with itself. This is a fully convolutional network, and since patches recur, it is much easier for the filters to learn how to create these patches with low entropy. But it's very hard for them to generate the noise with the high entropy with no correlation. It is able to do that. It can overfit, but it takes it more time. So this can be used for denoising, and they show other applications. For example, in painting. Let's say I have this image with missing parts. Now I can use this image, and once again, I'm just going to try to generate this image. So I'm going to do that, and I'm going to just use this mask. And the thing is that I'm going to get the image with the missing parts just because I trained on the non-missing parts, and then for the missing parts, I'm going to just apply the filters, and they're going to use what they learned from the other parts, and this is the easiest solution for them. I'm going to skip another application they do for super resolution, and I'm going to talk about our approach. So our main observation is that a lot of image processing applications can be viewed actually as image decomposition. Let's see one example. So taking this zebra image, we know that it can be reconstructed using this segmentation mask and this zebra pattern plus 1 minus the mask multiplied by the background pattern. And if we're able to do this decomposition, then we're able to do segmentation, because this mask is the segmentation mask. And similarly, Dhazing can also be viewed as a decomposition based on the physical model. There's the transition map and the haze-free image, and in the same way, also if we have these two images taken through some transparent glass or something, this is called transparency challenge, then what we have is one image multiplied by a constant and another one multiplied by 1 minus the constant. So these are classical challenges that we think that can all be viewed under this unified framework. So here is how double deep works. So let's say I have these two images combined and I want to separate them. So I'm going to use the deep image prior, but not just one. I'm going to use a couple of them. And I'm going to generate this image, which is a summation of both of my deep image priors. And I'm going to use a loss that says that I want to reconstruct the image. And as you know by now, this is a very easy task. I am able to generate this image. But the crazy thing is that now the way every deep image prior by itself worked is that each one of them actually generates the pure image, the pure unique image for itself. And the reason for it is that it is the easiest solution. Each network is fully convolutional, and patches recur more inside one image than across different images. So the easiest solution would be this. Now, we're not just taking the summation. We can use this mask saying for every pixel how much we want to take from each image. and we're going to also learn the mask, and we're going to use some exclusion loss that I'm not going to be able to talk about now, but you can also see how this works for segmentation. So I have these football players here, soccer players, and now I'm going to require that my mask is going to be a binary mask. And this is the whole difference now. I'm now generating, again, this image, but now I'm able to get the segmentation mask, and as a byproduct, I'm able also to get the soccer field without the players, and this really crazy thing that this is what happens when you take football players and you paint the entire image with them. So we're getting really nice, not state-of-the-art result, and this is not semantic segmentation, but we get really nice results for segmentation, and we are also able to do this for video. Here's some skydiving video, and we are able to do the segmentation, and this is what it looks like. And another special case of transparency separation is watermark removal. You have these companies putting watermarks on images. So we're able to treat this as if it was just two images. One is the watermark and one is the original image. And we're able to separate them. This is with some hint from the user saying about where is the location. But if we don't want to take the hint, we can just use several images with the same watermark, and then we're able to separate them so that we get on one side the clean images, and on the other side we get the recovered watermark. Lastly, I want to talk about dehazing. For dehazing, we're getting really nice results. So the separation is just the basic physical model, and we're getting results that are at least comparable to state-of-the-art. You can see by yourself, dehazing is a tough challenge to evaluate, but we're getting really good results using double dip. The only difference when we apply it for dehazing is that now we require from the mask to be smooth. It's not binary like in segmentation, and it's not just a constant like in transparency, but we want it to be smooth, and this is what helps us get this dehazing. We also introduced this really novel approach for dehazing because we're able to use non-uniform air light. Those of you who know the challenge of dehazing would know that this is the first time that it's done, and it's really a big advantage because you can see how in shady places the air light is different, and this enables us to produce much better results. So, if you have to remember only one thing from my talk here today, so it would be that one image contains tons of data, and that local patch distribution of natural images is actually the DNA of these images. And if you want to be able to generate a brother or a sister to your natural image, the best thing to do would be to capture its DNA and then replicate it. And the last thing is that every one of the methods that you've seen here is actually totally unsupervised and doesn't need anything, only the input image itself. So I want to thank you for listening, and if you have any questions, then I'll take them now.